Hi everyone, so in this video we're going to study what is probably our first perturbed version of a differential equation, and to do so I just picked an example of a problem which is a projectile equation. And so the problem we're going to solve here is about the motion of an object that is thrown from the Earth's surface, thrown up vertically, and the object is going to come down on the Earth after a certain time. All right, so the equation that governs this problem is just Newton's second law, mass times acceleration, and on the right we see forces on the body, which are just expressed here as Newton's law of universal gravitation. Right, so you recognize here the mass of the object, gravity times the radius of the Earth, and this is the distance between the Earth and the object. All right, so we assume here that x could be possibly large with respect to r, but what we're going to write in this problem is that x is something that is in fact not too large with respect to the radius of the Earth. All right, so if we would definitely neglect x in the right hand side, if we neglect x in right hand side, what we would obtain is mass times acceleration is equal to, so you see here, if we neglect x in front of r, the Earth radius, r square, they just disappear. So what's left on the right hand side is minus m times g. And so if we assume, we can integrate, of course, this equation, and it should yield something that is quite usual, minus 1/2 acceleration times t squared plus v0 times t. So we can also equip this problem with two initial conditions, which would be that the initial velocity is equal to v0, and at t0, of course, and the initial position is equal to 0. All right, so we recover something that is known, but we would like to know what is the first perturbation to that solution. Okay, what is the first perturbation to that solution if we account for small x, all right, but not neglect. All right, so you remember from the very first videos that you might have seen in the series of video A, that I discussed what's the difference between neglecting and assuming that a quantity is small. If we neglect, in fact, we return back to the unperturbed problem. All right, so what we notice here first is that a problem is not written in a proper dimensionless version, so we should use this exercise at the same time in order to practice our skills at writing a problem in a dimensionless version and introduce a small number. All right, so what we need to do here is certainly to find a characteristic time, and we need to find a characteristic position, characteristic time for sure in this problem, and a characteristic position. All right, so definitely the first thing we need is this and this. If I can just write characteristic time and characteristic position, we can list the parameters of the problem and see how many options we have. So we have the Earth radius in meters. We have the acceleration of gravity, meters per square second. We have an initial velocity, which is v0, meters per second, and that radiates. All right, so in this case, this is quite obvious how we can construct time scale here. We have two options: either we use r and v0 just to get rid of the length, and we obtained a characteristic time. So that should be r over v0, which corresponds to how much time it would need, the projectile would need to travel a distance equal to the Earth radius here, if it would keep the same initial velocity. Okay, that's option 1. And we have another option to define a dimensionless time, which is based on these two, and which would be based on the ratio of v0 and g. All right, so we have v0 over g. All right, so you remember that in the problem we should avoid using characteristic quantities which are related to everything that is small. Everything that is small, of course, relate also to everything that is large. All right, because r is large in this problem, we should avoid using r. All right, so I should avoid any characteristic quantity involving r. All right, so this means that a characteristic time is probably best chosen as v0 over g, and we need a characteristic length for x star. And so again, you see, we're going to avoid r. We could use r, but we want to avoid this one because x is small compared to r, and so we don't want to have a rescaled version of x that we're going to write in a moment. So I'm just going to write in a moment x as a function of time is equal to x star multiplied by a rescaled quantity y, and we would like to have y of order 1. All right, so you see that definitely if you choose x star as being equal to r, this is of order r, this is much smaller than r, so it means that y is not of order 1. Okay, so we should refrain from using this in the definition of the characteristic length. So we are just left with these two quantities, so we need to square this one and divide. And so the only option left we have for x star is v0 squared over g. All right, and so based on that, we can redefine rescaled quantity, rescaled unknown, which is x of t, our characteristic displacement multiplied by y as a function of the new time tau, which itself is a function of time t. All right, and the dimensionless time is tau equal to t over t star. All right, so this being said, now we can revisit the differential equation. So any derivative with respect to time will be 1 over characteristic time multiplied by a derivative with respect to tau. Okay, and we have the same, of course, for the second derivative. So the left-hand side, which is m, let me just simplify out by the mass, okay, because that will make things easier. So on the left-hand side, we have the second derivative of x with respect to t. So it's going to be x star over t star squared. You see, this is easy as soon as you think of units. We need acceleration there. It's the second derivative of x with respect to time t. So I'm using y double prime to indicate we have a second derivative of y with respect to tau. And on the right-hand side, this is equal to minus gr squared over x plus r. And x is x star y plus r, and this is squared. Okay, so we can probably substitute for x star and t star the quantities we have over there. So this quantity here is equal to v0 squared over g, that's x, and we need to divide by t star squared, which is v0 squared, and g squared over there. So in fact, this is equal to g. So it means that we can simplify this with that here. All right, so if we rewrite this equation, we have second derivative of y is equal to minus 1. Let me just divide both sides of the fraction here by r squared. So we have minus 1 over 1 plus x star over r times y of tau squared. Okay. And here, what we see is that the small quantity naturally comes in the problem. All right, and so this is the small quantity, you see, because we have characteristic value of x, which we want to say this one is small compared to the Earth radius. And so we can define epsilon is equal to x star over r. And that should do it. Okay, we could rewrite the governing equation, but we also need to rewrite the initial conditions. All right, so we started from this governing equation, and these are the two initial conditions, so we need to rewrite them. Second one is easy, right? Because x is equal to 0 at time t equals 0 means that y at time tau equals 0 is equal to 0. And the second equation is first derivative of x with respect to t at initial time is v0. So we have we can rewrite this in this manner. X star over t star multiplied by the first derivative of y at time tau is equal to 0 is v0. And so if we substitute again x star and t star like those, you see that the ratio of x star over t star is in fact nothing but v0, which simplifies out. All right, so the second initial condition is just that the first derivative of y is equal to 1. All right, so we want to solve second derivative of y is minus 1 over 1 plus epsilon y squared with initial conditions like those. All right, so you see that the formulation we end up with is quite simpler than what we had at the very beginning. And you see here all the benefits of writing the problem in a dimensionless manner, because we have simple expressions here and over there and over there and over there, which makes it quite neat. So it's way easier to understand exactly how a problem is featured as soon as it's written in such a format. All right, so at this stage we can discuss the different ways to perturb differential equations. Different ways to perturb a differential equation. All right, so we had seen that in algebraic equations, there's basically one way to do, is that you put extra terms in the algebraic equation, and those terms are the small perturbations. And that's it. And it can lead to singular or regular perturbation, and that's probably the only thing we could definitely discuss about that. As soon as we talk about a differential equation, there are different ways, and there are basically three ways to perturb the equation. First one is in the governing equation. In the governing equation. And that's the case we have over here, right? So we use epsilon in the governing equation, and that's one way to perturb the equation or to perturb the problem. Another option can give you just 1 second if you want to think about it and probably anticipate. This is not too tough. Specific to differential equations, of course, are boundary conditions or initial conditions. All right. So another way to perturb a differential equation problem is to give a perturbation in the initial or boundary conditions. Okay, that would mean in this case, it's not something that I've just written, but it could be, for instance, that instead of throwing the object from the Earth's surface, you could just throw it from, I don't know, from a certain point that is far above the ground, or a little bit above the ground, in such a way that instead of having here 0, it could be anything else, like, for instance, epsilon, or epsilon squared, depending on how you formulate the problem. All right, so that's the second option. That's something we will discuss a little bit later, and with other examples. And a third option is to perturb the problem at a different time, as soon as we talk about initial conditions, at a different time than the original time. All right, so that would just mean, let me keep coloring those. It means that you can perturb the problem at a different time, at a different time or position, if this is a differential equation with respect to space. Could be also other quantities, of course, where initial conditions or boundary conditions are imposed. All right, so this is either not something that we are going to discuss in this example here. So we are only going to tackle the first problem in this case. And in the following videos, there will be plenty of more examples of perturbations in either initial boundary conditions or at the time or position where they are applied. All right, and so what we need to do whenever we have this is this kind of problem is to, in a very standard manner, use an ansatz as we did earlier, and substitute in both, and that is important, the governing equation and the initial conditions or boundary conditions. All right, that's very important to consider the problem as a whole. So it means that the problem includes at the same time a governing equations and boundary or initial conditions. All right, so we can try to see what we can do with the problem at hand. All right, and so as usual, it's maybe not a big issue to first have a look at the unperturbed problem. Okay, as we started with the algebraic equation, so unperturbed problem. So the unperturbed problem would just say epsilon is equal to 0. So it means that we solve, you see the denominator here, then becomes equal to 1. So we solve second derivative of y is equal to -1 at any time, tau, with initial condition like these, okay? They are, in the unperturbed version, the initial conditions are not perturbed, right? So they don't change in the unperturbed version of the problem. So if we want to solve this, we can integrate once. Means that first derivative is minus tau plus a constant, but you see that when tau is equal to 0, we need to have the first derivative equal to 1, so the constant here is 1, and we can integrate once again. This is minus tau squared over 2 plus tau plus a constant, but you see that this constant needs to be equal to 0 because of that. And this, in fact, here is nothing but what we discussed earlier, right? It is nothing but this solution here. Exactly the same, but written in a dimensionless version. All right, so if you want, maybe we could try to compute x just to make sure we have exactly the same quantity. So x is x star multiplied by y. X star is v0 squared over g multiplied by minus tau squared over 2, and tau is t over t star. So this is t over v0 and g. That is tau, right? Tau is t over t star. So this is t over v0g, t over v0 n times g. So we have this squared plus t times g over v0. All right, and so we just have to simplify out things a little bit over there, and there might be a 1/2 missing here. So we have minus 1/2. You see we have v0 squared that drops out, g squared that simplifies. So we have 1/2 gt squared plus v0t. All right. Of course, this is the solution that we could get from the very early analysis that we made. All right. So let's assume here that we can use a regular ansatz looking for a regularly perturbed solution of the problem. All right, and so we can use an ansatz now that looks like this. The main difference between what we have now and what we had earlier is that in the ansatz we still have a sequence of epsilon, but each coefficient of epsilon is now a function of time instead of being a constant as in algebraic equations. All right, I stop here after the first correction term because in the initial process we just said we would like to determine what's the first correction to the leading. All right, and so I hope that just by substituting this in both the governing equation and the initial boundary conditions, we're going to get an expression for y1. All right, so if we do this, then we have on the left-hand side second derivative of y, which is like this. And then what I could do here, instead of keeping the denominator here on the right-hand side, I can multiply on the left. So I need to expand 1 plus epsilon y squared. And so this gives 1 plus 2 epsilon 0 y0 plus additional terms. And this is equal to minus 1. All right, so if we collect the different terms together, we have second derivative of y0 plus epsilon second derivative of y1 plus twice y0 prime prime. This is equal to minus 1 plus following terms which are of order epsilon square. All right, and we need to do the same for the initial conditions. In this case, it's not very complicated, but I like to take advantage of this simple example here because it's important for you to practice and make sure you do this every time. All right, and if this becomes obvious to you, then it means that you understand how perturbation methods work, and it becomes like a very fast reaction to you. All right, so the first condition is y0 is equal to 0, so it will give y0 plus epsilon y1 and so on. This is equal to 0, but you should keep in mind that this is like writing this all right, because we are going to balance the different powers of epsilon in the initial conditions as well. All right, let me go to the end. And the next boundary condition is first derivative. This is first derivative plus epsilon y1 first derivative. And this one is equal to 1 plus nothing, all right? Okay, that's a trap, or it's a mistake that I see sometimes in exercises. And if you write it this way, definitely you will notice that the initial conditions for y0 and y1 prime are definitely different. All right, so in summary, at leading order, we need to solve in the governing equation here, we have y0 prime prime is equal to -1 with initial conditions like this. All right. And at the following order, we need to solve y1 is equal to -2 y0 prime prime. All right, coming from here. And this is equal to 0. All right, so I just pushed this to the right-hand side. And now the initial conditions at order epsilon, this is y10 is equal to 0, and y1 prime is equal to 0 as well. Okay, and the biggest mistake here that you could make is to say that this is equal to 1 because you just copy-paste what you saw at the leading order. All right, but that would be definitely wrong. So we have as initial conditions, we have this, and first derivative of y is equal to 0. All right. So the leading solution has been solved already. So what we can do next is to solve the problem at first order. Sorry. So we have y1 is equal to -2 y0. So we need to introduce here the expression we got for y0. Maybe let me just copy paste in between. Y0 is what we got for the unperturbed solution. Okay, it was just over there. Okay, easy. So this is minus tau square over 2 plus tau. And then the right-hand side for y1 is minus 2 times minus tau square over 2 plus tau. And second derivative of y0 is -1. Okay, so let me just change the sign here. So we have twice tau minus tau square. All right, so we can now integrate this equation, which would mean the first derivative of y is equal to tau square minus tau to the third over 3 plus a constant. All right, and this constant here, we can use this initial condition to determine the constant. We see that the constant actually disappears. So here we need to integrate once more in order to get the expression for y1. y1 will be t to the third over 3 minus t to the 4 over 12 plus a constant. But again, the constant is equal to 0 because of the initial condition over there. All right, so if we put everything together, we end up with the final expression we were looking for y. This is tau minus tau square over 2 plus epsilon times tau to the third over 3 multiplied by 1 minus tau over 4. All right, so now we need to substitute the original parameters of the problem. Remember we said that epsilon was x star over r, which was introduced in here. All right, and we have x star is v0 square over g. So this is v0 square over g and r. And we have tau, which had been already computed earlier, which is g times t over v0. G times t over v0. All right, so probably we can compute here just this expression that comes over there. And so we have epsilon times tau to the third is v0 square over gr. We have g to the third, t to the third, and v0 to the third. All right, so if we put everything together, x is equal to x star times y. And so we're gonna have for x, well, the first two terms we did the job already, all right? So we can copy what we had before. That's what we have. And then for the remaining terms, we'll have things that simplify a little bit over there. One just v0 will remain here. Okay, so we don't forget, we need to multiply here by x star. So we have x star epsilon t to the third, tau to the third power is going to be, so we have a v0 squared, which simplifies here, so there's only one left. We still have t to the third, and we still divide by r, and there's a g square over there, which remains, which leaves us with just a simple value of g, simple occurrence of g in the numerator. All right, just a quick check, v0 square, g in the numerator, r remains, and t to the third. All right, so what we have here is v0 times g times t to the third divided by 3r and multiplied by 1 minus gt divided by 4 v0. All right, and that's it. And the extra terms that we have dropped are terms of order epsilon square, which means v0 to the power 4, g square, r square. This is it, and I think that was a very nice example to start working with perturbed differential equations. We'll see many more difficult problems very soon. This one was a regular perturbation of the equation because we didn't change the format of the equation at all by adding the perturbation. And we did expect to recover at leading order the solution that we would have obtained just by neglecting the perturbation in the original problem. All right, so I hope you enjoyed and keep watching the following videos so you'll discover much more about perturbed differential equations.